Welcome to an ultimate review on collecting data, getting you ready for the AP Statistics exam. Please don't forget to like this video if it helps you. I would really appreciate it. All right, so let's just dive into collecting data. Real quick here, try to make this as efficient as possible to get you ready for the exam. So we've got two overarching ways to collect data, through an observational study or an experiment. Now, an observational study could be literally just asking questions to get answers back from people, places, objects, animals, whatever it is. Or we could actually examine relationships between two variables, which means we're looking for how one variable affects another. Now, an experiment is another way that we can examine the relationship between two variables as well, but there's a lot more kind of rules there. But in a general sense, all of these different things are a way that we could collect data. Whether we're collecting categorical data or collecting quantitative data, we're getting data. Let's start off with very simple sample surveys. This is where we just want to get some information, whether it be the weight of bullfrogs or the opinions on if somebody's going to vote for a specific tax levy or something like that, right? So if you want to get samples, one way you could do it is, well, you could actually get a census, which is getting everybody. That would be the best case scenario, but sometimes the biggest issues with censuses is that they could take too long and they cost way too much money and time to actually collect. So the best thing we could do is say, let's get a sample. And samples can be really, really good if they are random, gotta be random, and they are representative of the population which they came from. So there are four really, really good ways to get samples. We can do a simple random sample, a stratified random sample, a cluster random sample, and a systematic random sample. Now, just to go over these, because one of the multiple choice questions almost every single year is going to be a scenario, and you have to choose which method was used to collect the data. Now, simple random sample by definition is every possible group of n objects has a chance to be picked. Easiest way to do that is give everybody in the population a number, use a random number generator, and randomly pick out as many numbers as you need. If you need 50 numbers, then you pick out 50 numbers, and you get those people, those animals, those objects, whatever it is that's attached to those 50 numbers to be in your sample. So through that, literally every group of 50 that you could possibly think of could be picked. Now, a stratified random sample creates groups that cannot be picked. And let me explain. So a stratified random sample, we first break our population down into groups. And we break them into what we call homogeneous groups, which means in each group, we want them all to be very, very, very similar. We want them all to be, well, the same. Now, why do we want them to be the same? Because what's going to happen is this. We're going to break our population into groups. Maybe we have all the red go in this group, all the green go in this group, all the purple go in this group, all the yellow go in this group. And then after we have our groups, again, they're all red, they're homogeneous. They're all purple, they're homogeneous. We visit each group and take some from each group. How do we take some from each group? Well, randomly. So essentially, we're going to do a simple random sample within each group. Now, what this is doing is it's going to get us that great representation, because under a simple random sample, we might all get red. Now, that might be very unlikely to get a sample that's all red, but if you stratify, take some red, some yellow, some purple, some green, some blue, you're not going to get all reds. That's why it eliminates that group from being possible, and it gives you that representation that you know and love. So the key thing is you break into groups based on something that they have in common. Now, how many do you take from each group? Well, that's actually up to you. If there's more red, you could take more from the red group, less yellow, take less from the yellow, but you do have to take some from every single group. Now, cluster random sample is when you also break your population into groups, but you break them into groups that are heterogeneous, meaning the groups are already nice mixes of all the different colors, for example. So maybe you have a group that's already a nice mix of reds, purples, greens, yellows, blues, whatever. And then you have another group, and another group, and another group, and the groups are heterogeneous within, which means they're already mixes within. And what I tell students is that when you do a cluster random sample, each cluster is in a way a mini population because it represents the population. Then what you do is you pick one or two of the clusters at random. So you're not labeling the individuals within each group like you would do in a stratified. What you're doing is you're labeling the groups. And then you're picking as many groups as you need. Maybe it's only one. Maybe you need a couple more so you get 2 or 3 groups. But the idea is you're not picking people at random, you're picking groups at random, and whatever group gets picked, well, since that group is already heterogeneous, meaning it's mixed up within, since it already is kind of like a mini population, it should therefore represent the population. The last one is the systematic random sample. This is where we pick, like, all right, we got everybody's in random order. Maybe it's a list on a piece of paper, something like that, or maybe they're in line at a sporting event, and you're going to say, okay, I'm going to pick every 10th person, or every 5th person, every 30th person. It's whatever, it's every kth person will get picked. So to be honest, the first and the last are pretty easy to recognize. A lot of kids mix up stratified and cluster. So just remember, they both involve breaking into groups, but how we create those groups, stratified, we want them to be homogeneous. We want everybody in each group to be very similar. Cluster, we want everybody in each group to be very different, heterogeneous groups. And then the second thing that makes them different is once you have those groups, what do you do next? Stratified, you take some people randomly from each group. Cluster, you just take one or two of the groups. Let me use an example here to really kind of have this make sense. Imagine we got 20 boxes and each contains 80 identical toy rockets. And we want to select a random sample of these toy rockets to maybe test and make sure they're working appropriately. Now, 20 times 80 is 1,600 total toy rockets. I could do a census and test them all, but maybe I'm like, I don't got time for that, so that could be a problem. The other thing I could do is I could do a simple random sample. So I'd actually have to unbox all 1,600 rockets, give each one a number starting at 0001, going all the way to 1,600, use a random number generator, or a random number table, ignore repeats, ignore numbers that no rocket has. Like if 1,862 comes up, well, nobody has that number, so ignore it. And then I would pick out, 50 rockets or 100 rockets, however many rockets I want to be in my sample. And that, again, is up to you as well. That would be a simple random sample. Now, stratified would be, okay, let's create groups. Now, oh, wait a minute. I already got groups. I got 20 boxes. Every box contains 80 identical toy rockets. Okay, so I already got groups. 20 boxes, each box is this group, and within each box, they're all toy rockets, so they're homogeneous. So then what I'm going to do is I'm going to visit each box. So I'm going to go to box 1, randomly select 2 rockets. Go to box 2, randomly select 2 rockets. Go to box 3, randomly select 2 rockets. So I'm going to have to repeat this to every single box. But at the end, I will have a stratified sample because I took some rockets from every box. Now, that would actually only be important if I thought that the box made a difference. Like maybe one box was made on Monday at 8 a.m. and that box could be different than the other box that was made at Tuesday at 9 a.m. or something like that. But the idea there is that I got these groups and I'm going to take some from each. Now, if I take 2 from each box, it's going to get 40. If I'm like, well, I need more, well, then take 3 from each box. But whatever it is, you're visiting each box and taking some out. But that's going to take a lot of time because every time you get to a box, you're going to have to label every rocket in that box 01 through 80 and then randomly take out 2 or 3 of them. And you got to repeat that process for all 20 boxes. That could definitely take some time. Now, how could I treat this as a cluster sample? Well, if I look at the 20 boxes as, well, my clusters, right? They're already into groups. In each box, I got 80 identical toy rockets. Now, you'd say, well, that's homogeneous. Yes, but all of them are identical toy rockets. All 1,600 are actually the same identical toy rockets. So in that sense, I could say, well, listen, it's not like the boxes are any different than each other. It's not like one has red rockets and one has blue rockets and one has large rockets and one has small rockets. They're all identical toy rockets. So in that case, my groups could therefore be looked at as my clusters. And then what I could do to save a lot of time, the big advantage here is just speed, is label the boxes 01 through 20 and then randomly pick out 2 boxes, and every rocket in those 2 boxes becomes my entire sample. Now, again, I want to emphasize, if you were like, well, wait a minute, some of the boxes are large rockets, some of them are small rockets, some are medium rockets, well, then you definitely want to do stratified, because if you take some from every box, you're guaranteed to get small, medium, and large. But if they're all the same already, why don't we just cut to the chase, save a lot of time, it's going to be a big advantage there, and do a cluster sample just taking some of the boxes. So a lot of times questions are going to direct you to understand the difference between stratified and cluster. So hopefully you understand that, but also understanding the positives and the negatives, right? In some situations, one could be better than the other, and understanding saving time, faster, those are all advantages. And sometimes you might be doing a cluster, but you're not doing it very well, and it doesn't represent the population. For example, if the 80 are the 20 boxes, where some medium, some large, some extra large, and some small. Well, the problem is if I do a cluster, the 2 boxes that I pick could both be smalls. Then all of a sudden, I don't represent the population. I thought I was doing something that was going to save me a bunch of time, but it wasn't smart because it didn't represent the population. So in that case, if I do have different boxes of different sizes, I definitely want to do a stratified. Now, systematic, I would also have to unbox all of the rockets, just kind of put them into random order, and then pick every 17th rocket or something like that. But that, again, also would take some time. All right, let's move on to talking about issues that lead to bias. Okay, this is another big topic, usually a couple multiple choice, and maybe even an FRQ could approach this topic. But there are 3 big things that could lead to bias in my world. First, we have selection bias. This is when your sample method is not one that I just talked about, right? Meaning it's not chosen randomly. Asking for volunteers is obviously going to be a problem because you're going to elicit certain responses. Usually when you ask for volunteers, you get people that feel very strongly one way or the other. Convenient samples, that is just picking at a sample that's convenient. Like, I'm just going to grab the first 50 kids I see because I don't have to do any extra work. Well, that's not going to be random. That's not going to represent the population. Another type of bias is what we call response bias. Response bias is when you get responses, but they're not truthful responses. So maybe you get the best, most random representative sample in the world, but the responses you get from those people in your very good sample are lies. Well, then now you have a whole nother issue. What could cause somebody to lie to you? Maybe it's the wording of your question. Maybe it's who's asking the question. Like, if my dentist says, do you floss? I'm going to tell him yes, when I probably don't floss as much as I should. But again, he caused me to lie because I didn't want to lie to my dentist. Or I did lie to my dentist because I felt bad, I guess is what I should say. Another method could just be like maybe you're measuring frogs and you're putting them on a scale to weigh their weight. But, that scale's broken. So every single measurement you have is untruthful because of simply a broken measuring tool. Now, another type of bias is non-response bias. This isn't necessarily the opposite of response bias, but non-response bias is, again, you get this great, beautiful, perfect sample, but some people choose not to respond. Maybe they just never email you back, or they never call you, they never mail something back to you, and that's a problem because maybe they're not responding for a very important reason, and that reason is what makes them representative, and which means you actually want to get their answer. So here's what we could do to fix non-response bias. We could call them again, we could email them, we could visit them, we could offer them an incentive as long as that incentive doesn't cause them to change their answer. Something that we could do to get everybody that got picked to respond is how we could get rid of non-response bias. But, for all of these issues that lead to bias, we can't just say, select more people. Get another sample, who cares? No, the sample was the sample. We need to fix it, okay? So ask good questions. Make sure you're covering all your protocols to make sure that you're going to try to alleviate any bias. Now, the AP test loves to ask about bias and then also ask about the direction that bias could lead to. So make sure you always think about, okay, if I don't get truthful responses, what type of responses am I going to get? Am I going to get things that go higher or go lower? So make sure you also think about the direction that your bias will lead your results to favor. All right, now, we also talked about an observational study in terms of looking at how one variable impacts another variable. So here's 2 great examples where an observational study could be needed. Does watching violent TV cause children to act violently? So first I have my response variable and my explanatory variable. The explanatory variable is the variable that is doing the impacting. So in this case, that would be the watching violent TV, yes or no. And then acting violently is the response to that explanatory variable of watching violent TV. Here's another one. Does not flossing every day lead to cavities? So cavities, do I have them? Maybe how many I have or how often I have them would be my response variable. That is because of or due to the act of flossing or not flossing. And again, that'd be my explanatory variable. Now, these can simply be observational studies because unfortunately we can't force people to floss every single day or not. We cannot tell people, hey, don't floss, and these people do floss because there could be a lot of other issues there. And then, you can't put a bunch of kids in a room and force them to watch violent TV. I mean, I guess their parents can okay, but that doesn't sound very ethical. But again, these are examples of observational studies. Now, observational studies are fantastic, But we can't use the word cause. We can't claim there's a cause and effect relationship. We could learn about associations. We can learn about tendencies. We can learn about relationships. But we can't say something causes another without an experiment. But just a quick overview of how an observational study would get done. Maybe you do pick people at random. You do get a good sample. And, you don't make them do anything, but you just say, all right, kids, thanks for being a part of this study. I'm so glad you got picked. Your parents all signed the release documents. What type of TV shows do you watch? And all you're doing is you're observing, you're taking notes, you're asking questions, but you don't make them watch anything. You're just asking questions to see who watches violent TV and who doesn't. And then you're going to say, all right, kids, go play on the playground or go to school. And I'm going to look at discipline records. I'm going to ask your teachers how you act in school. Or I'm going to talk to your parents. And I'm going to simply observe, do you act violently or do you not? And then I could put all that data together and find out, of those kids who do watch violent TV shows, do they tend to be in that group that acts more violently or not? Same thing with the flossing every day leading to cavities. I could get a group of people, maybe I choose them at random, and I just have them fill out a survey. Do you floss every day? Do you floss once a day? Do you floss every single day? Do you floss once a week? Do you never floss? And then I could track them into the future, maybe watch them for the next 5-10 years and determine if they get cavities or not. And then I could start to make relationships there. But again, I cannot use that word cause if it's purely an observational study. So the biggest difference in an observational study to an experiment, which we're going to talk about next, is that A, you can't use the word cause and effect, and you don't tell them to do anything, you just simply observe. Now, an experimental design is where we could actually, hopefully, if done properly, could claim that an explanatory variable causes a change in a response variable. So the example I have here for you is, does a new pill help lower cholesterol in men over 60 years old? So the explanatory variable is a new pill, and the response variable is hopefully my blood cholesterol being lower. Now, if I'm going to set up an experiment to do this, sorry for my terrible writing there, I need to make sure that the 4 pillars of a good experiment are all met. So let me talk briefly about them. First, comparison. Every good experiment has to have at least minimum 2 treatment groups. If I give all of the men in my experiment the new pill, and all of them have lower cholesterol or higher cholesterol or no change in their cholesterol, I'm going to learn nothing because they all got the same thing. I have nothing to compare them to. So at the very least, I need to have a second group of men that get, well, nothing. No new pill. Or maybe I have a third group that gets an existing pill already on the market to help lower cholesterol, and I want to prove if my new pill is better than that. But at the very least, I have to have 2 treatment groups. I could have 10 treatment groups, but I got to have at least 2 for comparison reasons. Now, control. Now, here we're talking about controlling all other variables. Now, other variables that could impact cholesterol, what we call extraneous variables. These are things other than my new pill that could help lower cholesterol. These are things like exercise, diet, genetics. The list goes on, but those are just to name a couple. Now, if you can control these things, well, then please control them. For example, if you could make all of the men in your experiment exercise every single day, well, then make them exercise every single day. That way, at the end of the experiment, everybody exercises. You can't say, well, those people got better because they exercise, and those people got better because they didn't exercise. No, they all exercise. But we also introduce another problem, because now all of a sudden my results could only be said to be true for people that exercise. If you don't exercise, I don't have any data on you, so I can't use you. So that's why exercise is one of those things that's hard to control. So maybe what you do at the end of the day is you say, listen, hey, some people exercise, some people don't. So actually I'm going to control for that by just having randomization, which we'll talk about in a second, put people that exercise in both groups and people that exercise not in both groups. The idea is that we want to have treatment groups. So here's my people getting the new pill. Here's my people getting, well, no pill. I want these 2 groups of people to be very, very, very similar. I want the people in this group to be very similar to people in this group, which means that I want people that exercise in both groups. I want people that don't exercise in both groups. I want people that have good diets in both groups. I want people with bad diets in both groups. That way, the 2 groups in of a sense are very, very similar. The only difference is, are they taking the pill or are they taking no pill? Now, there are some things that you do need to handle, like, hey, this pill needs to be taken in the morning with a full glass of water. So everybody's taking a pill, everybody's taking it in the morning, everybody's taking it with a full glass of water. Oh yeah, that pill contains 10 milligrams of whatever, chemical is in there, right? Those are things that I can keep the same. But things like genetics, diet, exercise, I can't control those, but that's where randomization actually controls them for me. So I actually say that randomization controls for the variables I can't control for. Hopefully that sentence makes sense. You might want to stop and say that to yourself and understand that. Now, what do we mean when we say randomization? Well, this is where we say, all right, listen, if I got 100 people, 100 men over the age of 60, how do I determine who gets the pill and how do I determine who gets no pill? Well, that has to be done randomly. So 50 men are going to get the pill, 50 men are not going to get the pill. Now, this is a question that's very common on the AP test. Just how will you do the random assignment? Easiest way in the world to do this, excuse me, is give everybody a number. 0, 0, 1 through 100. Everybody gets a number. Ignore repeats. Ignore numbers nobody has. Use a random number generator. The first 50 numbers picked get the pill. You know it as the researcher. You don't tell them what they're getting. And the remaining 50 people get no pill. It really is that simple. Don't overcomplicate that. Now, if you have a third group, okay, 33, 33, 34, whatever. Just make sure that some people get in each group and it's done randomly. And again, I really want to make sure why randomness is important here because it'll help evenly disperse the variables we can't control for. Say that one more time. Evenly disperse, hopefully, the variables I can't control for. So if I'm like, diet, I can't control people's diet, and I know diet affects cholesterol, well then again, if you do it randomly, people with good diets will go in both groups, people with bad diets will go in both groups. That way, at the end of the day, the two groups are similar. All right, now what's this replication? Replication could actually be a couple different things, but biggest thing is it is more than one. If I only have two people, one person gets the pill, one person gets no pill, I'm going to learn nothing. There are a million reasons why one person could have a lower cholesterol level than another person besides my pill. But if I have 50 people in each group, I'm going to have more power to see the truth. And if the new pill really does work, 50 versus 50, that's replication, having more people in each group, that's going to allow it to see it. You know what's going to be even better? Is if I had 10,000 people, 5,000 taking the pill, 5,000 taking the pill, or no pill, that's going to give me even more power to see the truth. And if the truth is that the new pill works to lower cholesterol, if I have 5,000 people all with lower cholesterols on average versus another group that did not take the pill, then listen, I have a lot of power to say that my new pill works. So that's replication. Another example of what replication could be is literally doing the whole thing over again with another group of people and then another group of people. But if you think about it, if I just repeat 100 people and then I get another 100 people, I get another 100 people, really what I'm doing is just putting more people into the pill group and more people into no pill group. And again, that's the idea of replication, is you have more power to see what's true when you have more people or objects or animals in your treatment groups. All right. Now, one last thing that's tied to this is a couple extra features of an experiment. So control group. Now, a lot of people think when we talk about the pillar of control, they think we're referencing a control group. That's actually not true. A control group is a group that gets nothing. Absolutely nothing. Now, is that group needed? No. If you want to compare a new pill to an old pill, then you don't need a group that gets nothing. You're comparing old to new, and that's it. You got your 2, which is your minimum for comparison. But oftentimes we do like to have a control group. That way we have a baseline group to compare to. So the biggest advantage of adding a control group to an experiment is that way you could have a group to compare to. Because maybe I find out taking no pill is actually better than anything. Like these pills on the market are actually bad for you and cause your cholesterol to go up. And the only way I'm going to see that is if I have a group that gets nothing. So you don't have to have a control group, but they can add some value to an experiment. Now, double or single blinded, double blinded is when the subjects that are getting the pills do not know which pill they're taking. And the evaluators who are actually going to measure their cholesterol at the end, they don't know either. That is blinding both the evaluators and the subjects. That's double blinded. Single blind is when you can only blind one of those groups for whatever reason. Now you say, well, how am I going to blind people here? Well, this is where I'm going to use the placebo. I'm going to give everybody a pill. But the people in the no pill group are actually getting a fake pill, which is a placebo. But we use a placebo to control for the placebo effects. The placebo effect is this human nature that the moment you get something, you think it's going to work. You think it's going to make you get better. And if you don't give me something, I'm not going to think about getting better. In fact, I'm going to think about getting worse, and all of a sudden my cholesterol goes up. So the placebo effect is just an idea of human nature that there's nothing you could do about. So the only thing we could do is control for it by giving everybody something. Everybody goes home with the pill, but they're blinded because all the pills are plain white little pills. I know who got what pill that's actually the new pill. I know who got the fake pill, but they don't. That way, everybody goes home thinking they're getting something. They're blinded because they have no idea what it is they're getting. They're just told to take this pill every morning with a full glass of water at 8 a.m., but I know who's getting what. Now, if you're working with animals, you're working with objects that don't have brains, you probably don't need to use a placebo because they aren't going to know the difference. But when you're working with human beings, we usually like to have a placebo for a group that is getting nothing to compare to. All right. Now, lastly, we have a couple different ways you could design an experiment. The first is a completely randomized design. This is actually what I already explained earlier. 100 people, 50 get the new pill, 50 get no pill or a placebo. Boom, that's completely random. Now, block design is when you're like, you know what? This idea of exercise, I just can't leave it up to randomness. Exercise is just so important. I know exercise changes cholesterol, so I can't just say, well, let's just cross my fingers and hope that people that exercise and don't exercise are in both groups. It's just far too important. So this is where I'm going to have to do a survey. Of my 100 people, I'm going to ask them, hey, who exercises, who doesn't? Maybe 20 exercise and 80 don't. Okay, I can't control that. It is what it is. That was done through just a survey. Then I'm basically going to run 2 experiments. Of the 20 people who exercise, 10 randomly get the new pill, 10 randomly get no pill. Of the 80 that don't exercise, 40 randomly get the new pill, 40 randomly get the no pill. Now, at the end of the day, I still got 50 people taking the pill, and I still got 50 people taking the placebo. But I specifically broke it down by exercising and don't exercising. This guarantees, it's no longer randomness. This guarantees that each group of 50 people, 50 getting the pill, some exercise, some don't, 50 people that take the placebo, some exercise, some don't. This guarantees it. Where randomization, we just cross our fingers and hope. This guarantees it. That's the idea of blocking. So you create blocks, and then within each block, half get, this and half get that and so forth. Now that, of course, needs to be done randomly. Now, matched pair design would be when you are like, wait a minute. There are far too many extraneous variables that I don't want to just leave up to randomness. I got genetics, I got age, I got exercise, I got diet. So this is where you say, all right, I'm going to pair people together. So maybe I create pairs of Tom and Bill. Why are Tom and Bill a great pair? They're both 65 years old. They both exercise. They both have good genetics, meaning that they're not predisposed to any kind of high or low cholesterols. But you know what? They both have poor diets. The idea is they're very, very, very similar. Now, one of them gets the new pill, one of them gets no pill. They don't know because they're blinded. I'm going to use a placebo for the guy that gets no pill. And they're not the only group, by the way. I got another pill of, another pair here, of Henry and Connor, and then another pair, and another pair, and another pair, and another pair. And in each pair, somebody gets the placebo, somebody gets the actual pill. So at the end of the day, guess what? I still got 50 people taking the pill, and I still got 50 people taking the placebo. But now I created these pairs where I could literally take Bill and compare him to Tom because they're so similar. And I could really see, hey, did the new pill help one of them have a much lower cholesterol? Because you can't blame it on anything else because they were so similar. Twins make great pairs as well if you can do that. But the idea is, truthfully, a matched pair design is just a super advanced form of blocking where you have very small blocks of 2 people only, and they're very, very similar for many reasons, and then within each, one gets one, one gets the other. So now, and oftentimes another question that comes up is, how are you going to assign the treatments in a matched pair design? Well, it could be something as, hey, listen, assign them each a number, 1 and 2. Use a random number generator. If the first number that comes up, they get the pill, the remaining number doesn't get the pill. They don't know, but I know who's getting what. Or you could even flip a coin. Heads, Tom gets the placebo. Tails, it's Bill. Toss the coin, the other person automatically gets the pill versus the placebo. But again, you do that behind closed doors. They don't know because you want them to be blinded. The only issue with matched pair design is you can only have 2 treatments. If you have new pill versus old pill versus no pill, that's 3 treatments. You can't do a matched pair design. You have to do 2 treatments only. So that's the only drawback there. All right, hopefully those design types make sense. The most important questions that you may see is just reading a multiple choice question. You have to decide which type it is. That's very popular. Or on an FRQ, you pick a design or one is told to you and you have to talk about how you're going to actually do the assignments. Now, I've also seen lots of multiple choice questions that just go over the importance of control, the importance of replication. Hey, why is it important to have replication? Well, like I've already mentioned, the more people in each group gives you more power to see the truth, to see what's actually going on. It's very difficult if it's only 1 versus 1. Randomization, remember, randomization is important because it controls for all the other variables you cannot control for, making your 2 treatment groups as similar as possible, other than what you are giving them, pill or placebo. So hopefully this video did a great job just quickly reviewing a lot of these key concepts when it comes to collecting data through an observational study, sample survey, or even experimental design, to make sure that when you approach one of these problems on the AP test, you have a quick reference point of what needs to be said and why. All right, if you have any questions, please feel free to hit me up in the comments or send me a message. Good luck on the tests.